Greetings and welcome, friends. Mr. Waddy here. We are continuing our lesson on solving equations, plural. We'll do more than just one, with variables on both sides of the equal sign. So big idea, step one is simplify, which means distribute if possible, combine like terms, and then we move the little guy to the big guy and use inverse operations to get the variable by itself. So step one in this case, this example, before we jump into new stuff, is distribute. So I'll distribute like so. -3/4 times 8n. Oh my goodness, fraction work, friends. So let's see. I could do 3 times 8, get 24, and then divide by 4, which is 6 with a negative. Or you can do division first. This is actually the way I like it. Watch this trick. This is going to help you out with fractions. 8 divided by 4 is 2, and now do the 2 times the -3 is -6n. Let's try the same thing for the 12 here. Instead of doing 12 times 3 and then dividing by 4, let's do division first, because division makes things smaller, right? So 12 divided by 4 is 3, and now 3 times a -3 is -9. Okay, so also check out my man Khan if you want some fraction help multiplying fractions. That would probably be a good video to check out. 3 times n is 3. 3 times -3 is -9. Right? So now I've simplified. I don't have any like terms I can combine. Actually, let me ask you guys this question. Why can't I combine these like terms like so? Yeah, they're on opposite sides of the equal sign, so I can't combine them like that willy-nilly. I've got to move one to the other. I can't combine them as is. So who do you think I should move? -6 is smaller than +3. You're not wrong for moving the 3n, by the way, but I always like to move the little guy to the big guy. So add 6n to both sides. Right, you with me here, Austin? You with me? 3 plus 6n is 9n. And actually, my buddy Austin, he did a cool trick on his homework that I liked a lot. He noticed 2 things that were the same term on different sides of the equal sign, and then he just kind of like zeroed them out, which I thought was a pretty clever move. And he did it with variables. There was a problem the other day where we had like a 3x, a bunch of other things equals, and there was a 3x and some other things, and he just like zeroed these out. And I thought that was a pretty clever move that I have not shown you guys how to do yet. And in this case, I could do the same thing. I could just be like, let me just get rid of this -9 and this -9, change them to 0. But the reason that works is if I added 9 to both sides, I would get 0 equals 9n, and now I can get rid of the multiplication by division. It looks like a G, but that's fine. And flip it, reflexive property, so I'm just flipping it horizontally. N is going to equal, let's see, 0 divided by 9 is 0. 9 fits into 0 times. It doesn't even fit once or a fraction of times. So I get n equals 0. So there we go. So that's like one of the classic problems we've had. But now I'm going to show you something new. Special solutions, or lack thereof, when we're solving equations. Now, sometimes algebra problems, so far we've had a convenient one solution per problem, right? N equals 0, x equals 2, y equals 3/4, right? We've had one solution every time. It's possible later on, and especially in Algebra 2, maybe even actually this course as well, we'll have problems with 2 solutions. 2 solutions are possible, where you would say x is this or that. Actually, even tomorrow, with absolute value, we'll have that. And then quadratic equations later on. And today, we're going to take a look at cases where you could have no solution, or cases where you could have infinitely many solutions. Oh my goodness, is that terrifying to any of you? That sounds like a lot of work, but you'll see it actually won't be that bad. So special solutions of linear equations. Equations do not always have one solution. Wow. An equation that is true for all values of the variable is an identity. So if every number that I could ever plug in for x works, then everything is true for that equation. It has infinitely many solutions. An equation that is not true for any value of the variable has no solution. Okay, so we're looking at cases of infinitely many solutions and no solution. And they're going to have similar results when the algebra exposes those situations. And I'll just show you how to discern, how to determine how that works out. Let's see, I actually can't even show you a graph of how that works out just yet, but that's fine. So here we go. Here's some regular algebra problems that we would just be like, solving, and then it's going to go crazy, and it'll look like the world collapses on itself into some black hole abyss of mathematics. But that's fine. Don't you worry. So let's see. So we're going to simplify this. So here we'll do part A, the distributant. So I'll get 3 times 5x is 15x. 3 times 2 is, what's 3 times 2? 6, yes. And remember that this is multiplication by everything inside those parentheses equals 15x. Let's see, let's move the little guy to the big guy. Who's the little guy? Wait, well, okay, let me ask it this way. Who's the big guy? Guys. This is like when you're watching like an anime or something and you have two perfectly equally opposed forces, right? An unstoppable force and an immovable object, and then they like go and like fight and fly into each other, and then like there's just an explosion where it just decimates the landscape around them, and they're just like neither of them are hurt because they were equal and opposite forces. Yeah, what happens when I move the little slash big slash equal guy to the other side here? Let's see what I get. I'm gonna get, let's see, 15x minus 15x is 0, so I get 6 on this side, equals 15x minus 15x is 0 x's or 0. So what's x equal to? I don't know. I got 6 equals 0? Is that the answer? Well, actually, even if I did that, I'd move this over here. I would have had a minus 6 over here, and then I still would have subtracted 15x, and I'd get 0 equals negative 6. Huh. So question, is this a true or false statement? This is, oh yeah, false. That is not true, right? Well, I just said double negative. That is not true. That is false. So it's a false statement. And what this is telling me is that no matter what number I plug in for x here, this equation is never going to be true. You can just never make this person happy. We did all of the algebra, we did everything right, and then the girl still dumped me. Like, I don't get it, guys. I did everything right. Aren't I a good person? I'm trying here, guys. I moved variables, I distributed, I did everything right, and I'm still not good enough for this problem. Thanks a lot. Well, it turns out that no solution is my answer. Okay, so no solution. And the way that looks is when your variables disappear. Let's see. So variables disappear. Let's see. Now let's see. 1s double p ear, right? I think I got it. That's fine. I'm not worried. And you are left with a false statement. Right, so if, in this case, all of my x's just canceled out, and then I was left with a statement that was untrue, my conclusion is that there was no value of x that ever would have made them happy. Okay, let's look at this next example. We're going to practice a few of these, so don't you fret. Let's see, start with distributant. So I'll have negative 2 times 4y is negative 8y. Negative 2 times positive 1 is negative 2. Equals negative 8y. Huh, I feel like I've written this before. Guys, I think I found a glitch in the matrix, like deja vu. Wow, this is weird. Okay, let's move the little guy to the big guy. The little guy is the All right, how about no, let's move the big guy. No, let's bring everything to the big guy. Let's just try to move the same guy to the same guy. Here we go. Well, just you wait. Oh, this one's going to get interesting. The y's cancel out here. I'm left with -2. The y's cancel out here. I'm left with -2. I get -2 equals -2. So it's like someone asked me a question, when did Columbus discover, quote unquote, America? And then I'd be like, oh, -2 equals -2. He'd be like, that's a true fact, Brian, but that's not what I asked you. That's actually not helpful to me. Are you just being like a jerk? And it'd be like, well, I tried answering the question, and here's a statement, but that told me nothing about why. And it turns out there are infinitely many solutions here. Infinitely many solutions. Okay? So it turns out any number you can think of, if I was to do a check, if I plug in 1 for y, if I plug in -7 for y, if I plug in 10 to the 10th power for y, if I plug in pi for y, the square root of 7 for y, all of them work. Everybody works for this equation. This problem, it is just happy. It says, you know what? It's just like the Oprah of problems. It says, look under your seat. You're right for this problem. You're right for this problem. You're a solution to this equation. And just every solution works. And so notice these two problems are similar, where the variables disappeared, right? They canceled each other out. Except in this case, I was left with a true statement. All right? And that means no matter what I plug in for y, it's going to work. And since everything works, the way we describe everything in the world of math is with the word infinity. There are infinitely many solutions. So if we are left with a true statement, so left with a true statement, we'll end up looking at these graphically as well later on when we have that ability. But yeah, so right now, the way you do this, when you're solving a problem and your variables disappear, all you've got to figure out is this false or is this true? If it's false, there is nothing that will ever make this problem happy. It's just like, you know, just this negative person where nothing's ever good enough for them. And if it's true, then like this person's just like, that's fine with me. I'll just roll with it, man. Like just anything works for me. I don't care where we go to eat tonight. I'm happy. Right, and so that's the two types of cases we're talking about today. Let me give you one more situation here, one more example of this. Yes. Yeah, this one will do. We'll do one quick example, and then we'll jump into some problems of the words. So here we go. All right. So step 1, distributing. Right. And those are pretty good arcs. I'm happy with those. 3 times 2a is 6a. 3 times -2 is -6 equals 2 times 3a is 6a. 2 times -3 is -6. Uh-oh, deja vu, guys. Move the little guy to the big guy. Subtract 6a from both sides. I get -6 equals -6. True or false? Not a trick question. Is it true? Bless you. Or is it false? True. I mean, you saw I selected the green already there as well. Therefore, what is the solution to this equation? Everything is the solution to this equation. There are infinitely many solutions. Here, well, let's try a solution. Okay, when my variables disappear and I'm left with a true statement, there are infinitely many solutions. Let's try 0. All right. I'll plug in 0. 3 times 2 times 0 minus 2. Here, is that equal to 2 times 3 times 0 minus 3? Okay, 2 times 0, what's that? Let's see. Okay, here we go. 3 times 0, what's that? 0. Okay, all right, here we go. 0 minus 2 is -2. 0 minus 3 is -3. 3 times -2 is -6. 2 times -3 is -6. It works. Let's pick a different number. Let's try 1. Let's see. Let's do 3 times 2 times 1. Is that equal to 2 times 3 times 1 minus 3? Okay, so let's see. 2 times 1 is 2. 3 times 1 is 3. 2 minus 2 is 0, so I'll have 3 times 0. 3 minus 3 is 0. I get 0 equals 0. And it turns out every single number you can think of, fractions, decimals, negatives, positives, massive numbers, well, that's the issue with these problems is my letters disappeared. Okay, right? In both of these cases, when I did that, I got 0x and, right, 0 x's here. Like my variables all disappear. So in these special cases, when you notice your variables disappear, if it's a false statement, there's no solution. If it's a true statement, there's infinitely many. Okay, so that's the idea. So what you're doing is then analyzing the result, even though it's a really weird result. Here, let's do this word problem, friends. Let's use these variables on both sides to create equations that model real world situations here. Okay, so here's a boat, a tugboat by the looks of it. Boat leaves New Orleans. Oh my goodness, guys, these are like those nightmare math problems from cartoons on Nickelodeon. Oh my goodness. And travels upstream on the Mississippi River for 4 hours. Okay, I'm gonna highlight these. We'll do time for this. 4 hours. The return trip takes only 2.8 hours because the boat travels. Ooh, here's a speed. We'll do speed in red. 3 miles per hour faster downstream due to the current. How far does the boat travel upstream? That's a question about distance. Okay, how far is distance? Okay, all right. So this was craziness, right? Now I've got to come to the table with an equation. Does anyone know an equation that relates the variables rate, time, and distance? Does anyone know an equation that relates those things from physics or middle school math, science, whatever you've taken? Turns out there's an equation that says rate times time equals distance. Okay, so this is rate, time, distance. And it turns out, because math is the language of the universe, if I come to the table with the equation that represents life in this moment, I can then plug in things, I can relate things, I can compare things, I can solve things, and then answer this problem. Okay, so let's see. What do we got here? Now, how does the distance that the boat traveled upstream compare to the distance it traveled downstream? Let's see, it travels upstream for 4 hours, and then it said return trip. You guys agree, right? If it returned to the location that it started, I'm going to guess that distance upstream, all right, if it traveled, let's say it's 5 miles up the river, how do you think that relates to the distance downstream when it goes back to its original destination? How do these two values relate? Is one bigger than the other? Well, let's see. Let's think of this picture. Here's my map. Let's see. Here's a village. What's a village on the river? Springfield, Mass. And here's Brattleboro. Sorry, Springfield, Vermont. Here's the Connecticut River. Right. Here's the river. And our boat leaves Brattleboro, goes upstream, and comes to Springfield, right? And then later it leaves Springfield and comes downstream and goes to Brattleboro. How do those distances relate to each other, do you think? They're the same distance, right? I agree. So I'm going to say these two things must be equal. All right? These two things must be equal. That makes sense to me. So what I'm going to do, let's see, it says how far does the boat travel upstream? Let's define a variable here. Let's see, I currently know the time. Actually, this is how I'm going to do things. This is going to be awesome, all right? This is going to be awesome. Let's think about our variables and our units. So for my variables, let's see, let's think about upstream and downstream. Okay, so up, down. All right. Distance between those two things were equal, although we don't yet know what they are. How about time? Let's see. Upstream, it takes 4 hours. Okay. Downstream, it takes 2.8 hours. All right. So I'm just trying to like organize. There's a lot of information going on here. I'm trying to organize this all together. Let's see. What do I know about speed? I know that speed, let's see, the boat travels 3 miles per hour faster downstream due to the current. Okay, so when it's going downstream, it's plus 3 miles per hour compared to the downstream one, right? So let's see, I don't know how fast, or sorry, I don't know how fast it was traveling when it was going upstream, do I? Let's just call that x. So we'll call that x miles per hour for my speed, right? Or my rate. My time, let's see, distance we were doing in blue, and my time I was doing in green. Okay? So if it's traveling x, some unknown miles per hour when we go upstream, downstream it's traveling 3 miles more, 3 miles per hour faster or more than that. So I'll call this x plus 3. You think that makes sense? Yeah? And then like we've already said, distance and distance, even though we don't know what those are, we know they're equal to each other. So let's write an equation here. We don't know. And actually what's interesting is we actually won't need to know right now, but that is the question that they're asking. That's what they said. How far does the boat travel upstream? Which we've said, you know, I guess like the riddle answer would be the same distance it traveled downstream. But we're actually going to end up with that distance in miles. So here we go. Rate times time equals distance. Distance equals distance in this case. I'll work with yellow. I usually work with yellow. So if the distances are equal, this distance is going to equal the rate times the time. So 4 times x. This distance is equal to its rate times time. 2.8 multiplied by x plus 3. I should probably say that as the sum of x and 3. I've got to add those together before I multiply. So I've plugged all that in. Here is an equation in terms of a variable, which in this case is the speed of the boat traveling upstream. It relates to quantities, and now I'm going to solve this equation. So define our variables, write our equation, solve. How should I solve this? What's my first move? Right? I know you're not as familiar with all the work that I've just done, right? But you guys, if I just gave this to you to solve, right, that's just like the problems we did last night and earlier. How do I solve this? Yeah, I distribute. Let's see. Uh-oh. I might have to reach for a calculator in this case. Actually, you guys got some calculators. You're quick on the fingers. 2.8x plus 2.8 times 3. Let's see. 3 times 20 would have been 60. 3 times 8 is 16. Is that 7.6? I think. Maybe. I'm going to call it that. All right. Actually, I can cheat. Oh, I did it wrong. Wait a minute. Whew. Guys, I did it wrong. 3 times 2, right, 6. So 60, or is what I was thinking of. 3 times 8 is 16. 7, no, 7 point. 6. Why are they getting 8.4? No, because 3 times 8 isn't 16, guys. Oh, classic mistake, Mr. Waddy. 3 times 8 is, yeah, 24. So, yeah, 8.4 is what that ends up being. All right. You could reach for a calculator for that with no shame. Don't worry about it. So let's see. Now I've got variables on both sides. So what do I do? Little guy to big guy. Who's the little guy? Little guy? Who's... Yeah, so let's move that. Subtract 2.8x. And I'm going to get, let's see, 4 minus 2.8. Well, I like it. Yeah, wow. 1.2x with the arithmetic equals 8.4. And now how do I solve for x? Being multiplied. So divide both sides by 1.2 is the order we'd say that in. X equals, and it looks like this is just, what is that? I was going to say 4. Why was I going to say 4? 7. 12 goes into 84. Man, you were quick on the arithmetic, friend. So I get x equals 7. What did x equal in my problem? X was a speed, right? So 7 is what? 7 miles per hour was the speed that it was traveling upstream. They asked me the question, what? Distance, how far upstream? So if I want to find out the distance it traveled upstream, well, I know that 4 times x is going to equal distance. So I'm going to write, let's see, 4 times 7 will equal my distance. What? Well, let's see. 4 times x is equal to the distance, so 4 times 7, the solution I just got. So I'll get distance equals 28. And what measurement do you think distance is in? Let's see. Time was measured in hours. The rate was in miles per hour, so distance must be measured in miles. Okay? So my answer, BESA, my answer that I write is the boat travels 28 miles upstream. Now, guys, this problem had a lot going on in it, but that's why I want us to just kind of keep kind of practicing these concepts, rehearsing them, so that we'll be able to get the idea. Yeah. So the things that you had to know in order to do this problem was this formula, rate times time equals distance. You had to bring that to the table. You had to kind of be able to analyze the problem and figure out the rate, the time, and the distance in both of those situations. We had to recognize that those distances were equal, and because of that, I could then set these two equations, or expressions rather, equal to each other, and then the algebra showed up where we knew how to solve things. Okay, so it is a tricky problem, but hopefully with this example, you'll be able to do the one that you'll have tonight. All right, so thanks for watching, internet friends. Tienen un día el más bien del mundo. Have a day which is the most good in the world.